Let's look at the structure of hydrogen atom, the energy levels. So, hydrogen atom, what kind of Hamiltonian is it? It's simple. Hydrogen has one proton and it has one electron around it. So the potential it fills is the Coulomb potential with just one electron, one positive charge. Not hard. When you solve it, somewhat difficult. You get the energy eigenvalues, and it turns out to be En equals minus Rydberg over n squared, where Rydberg is minus 13.6 eV over n squared. Okay, and it turns out there are three quantum numbers, n, l, and m. N is the principal quantum number, L is the total angular momentum of the electron, and m is the projection of total angular momentum on the z-axis. Okay, that's simple. Another cool fact is that you can treat all the atoms in the first column of the periodic table. So say this is the periodic table. You can treat all this first atom hydrogen-like. The reason is, if you look at the second atom, which is sodium, I believe, it has one valence electron, meaning it has one electron in its outer shell. All the other electrons are packed inside, in closed shells. So you can't really access those packed electrons. You can play around with the electron that is outermost. So let's turn this hydrogen atom into sodium or something. So you have, say, bunch of positive charges in there, and this is the closed. There are negative charges, that are electrons there, and then there is the one valence electron that's outside. So all of this is not accessible, but at very high energies, not for normal energies. So what's the total charge of this entire cloud? Well, it's +1, because if you had 10 positive charges, you would have 9 negative charges plus that 10th one. So it's exactly like hydrogen atom. It has the same Hamiltonian. So it also has these energy eigenvalues. Now, this energy eigenvalue has a lot of corrections. For example, the electron, if you put yourself in the electron's frame, then you see this positive charge going around you. When a charge moves, it produces magnetic field. Since electron has magnetic dipole moment, it will feel a force, and that force comes because of the Hamiltonian minus mu of the electron dot B produced by the motion. This is internal magnetic field, and that internal magnetic field turns out to be proportional to the angular momentum of the electron. So this turns out to be of the form S dot L. So now the spin of the electron and angular momentum of the electron are coupled with each other. So you won't be able to know the z component of S and z component of L at the same time. They are coupled with each other. So the total, you can define this value called J, which is the total angular momentum of spin and the angular momentum, position angular momentum, and you can define J. So now you have different set of quantum numbers. You have N, you have L, you can still know L, you can know J, which is S plus L. You can obviously know the spin, but in the previous case, you could know ML, which is the projection of L on the z-axis. You could also know S, and you could have also known SMMS, the projection of spin on z-axis, meaning spin up or spin down. So you see that ML and MS you no longer know. Instead, what you know is the projection of the total angular momentum, MJ. And now the energies don't only depend on N, but they also depend on J. So let's just write that energy now becomes function of N and L and J, not L, J. Okay, so that was that's when we realized that the spin and the angular momentum interact with each other. Now, in case of atoms, other atoms, when you go down, the nucleus of the atom has its own angular momentum, and it's called, the nucleus is angular momentum I. And then obviously it turns out that this angular momentum interacts with the electron and the electron, so the Hamiltonian again becomes of some form which is proportional to the J dot I. So now it turns out you can't know J, because now J and I are coupled with each other. So you have to get rid of this G, knowing this Mj, and you have to define another quantity. In this case, we call it F, which is the sum of J plus I. Okay, so what are the good quantum numbers now? It's N, it's N, it's L, it's J, it's S, it's F, and now it's MF that you know. Now, saying something like it's a spin up or spin down doesn't make sense, because all you know is the total momentum, angular momentum, spin angular momentum of the nucleus, all that combined. And the energy levels now depend on different values of N, J, and F. You can have different effects. Now, when you have external electric and external magnetic field, then you get different splittings of energies, and it becomes even more complicated or more fun